Begin by talking about what computers can and cannot do. Computers operate deterministically. What this means is that they must have instructions fed to them in a specific order as they make decisions. The rules for these decisions have also been given to them in the form of instructions. And as a result, the same exact data, if it is given to the computer over and over again, then the decisions will be exactly the same, and the results, the outcome, will always be exactly the same. So, although there are clever computer programmers that can create the image or illusion of human consciousness, computers actually have no imagination or creativity or intuition or even a sense of humor. And even though Windows 8 might convince you otherwise, computers are not cruel or vindictive. They have no secret agenda or purpose. In short, they have no free will of their own. So let me show you a couple of YouTube videos that are related to this concept. Now I've posted these on Blackboard so that you can view them in their entirety under week 3. But I want to present a few of them here because they make sense out of this concept of having deterministically performing computers. Here we are. Sorry about that. So the first one I want to show you is from the 1968 film 2001: A Space Odyssey. And the concept here is that, or the background is that HAL 9000 is acting decidedly non-deterministically. Here's sort of a recap of what's happened up to this little scene. HAL 9000 is an artificial intelligence computer system that controls the life systems on a spacecraft called the Discovery 1. And HAL has like cameras, microphones, and speakers throughout the ship so that it can interact with the ship's astronauts. Now, when HAL begins to behave erratically, the astronauts decide to have this little conversation out of the range of HAL's microphones about shutting down HAL so that he doesn't jeopardize the mission. So let's take a look at what happens after that.
Open the pod bay doors, please, Hal. Hello, Hal, do you read me? Hello, Hal, do you read me? Do you read me, Hal? Do you read me, Hal? Hello, Hal, do you read me? Hello, Hal, do you read me? Do you read me, Hal?
Affirmative, Dave. I read you.
Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What's the problem?
I think you know what the problem is just as well as I do.
What are you talking about, Hal?
This mission is too important for me to allow you to jeopardize it.
I don't know what you're talking about, Hal.
I know that you and Frank were planning to disconnect me, and I'm afraid that's something I cannot allow to happen.
Where the hell did you get that idea, Hal?
Dave, although you took very thorough precautions in the pod against my hearing you, I could see your lips move.
All right, Hal. I'll go in through the emergency airlock.
Without your space helmet, Dave, we're going to find that rather difficult.
Hal, I won't argue with you anymore. Open the doors.
Dave, this conversation can serve no purpose anymore. Goodbye.
Hal? Hal?
Okay, so we see a definitely non-deterministic behavior in Hal because he was able to read lips even though he was never programmed to be able to read lips. And of course, that's not technologically possible. Hal can only do those things that it was programmed to do. Um, Another example would be a real world example that we see today. It's a artificial computer called Watson, and the makers, IBM, of this computer decided to create an artificial intelligence computer that would be able to compete in the game show Jeopardy. And I'll show you just a quick bit of this one. I'll cue it up to about 7 minutes into the video.
Which player would select first? Brad, you won that. So if you're ready, make your first choice.
Let's take alternate meanings for 200, Alex.
4-letter word for a vantage point or a belief. Brad.
What is a view?
Yes.
Alternate meanings 400.
4-letter word for the iron fitting on the hoof of a horse or a card dealing box in a casino. Watson.
What is shoe?
You are right. You get to pick.
Literary character, APB, for 800.
Answer the Daily Double. Now, Watson, although you have but $400, you know, of course, that you can risk up to the maximum value of a clue on the board, and that is 1,000.
1,000, please.
All right, here is the Daily Double clue for you. Wanted for killing Sir Danvers Carew. Appearance pale and dwarfish. Seems to have a split personality.
Who is Hyde?
Hyde, yes. Dr. Jekyll and Mr. Hyde, either one acceptable. You're now in the lead with 1,400. Go again.
Beatles people for 200.
Okay, so that gives you enough of a sense of what Watson is doing. He actually goes on to trounce the two former champions of Jeopardy, and you can watch those episodes of Jeopardy in their entirety. I've again posted them on Blackboard. So we'll discuss Watson in more detail later, but what I want to do now is just shift gears and talk about the five-step sequence that's the basic operation of the computer, and it's understood, or best understood, if we just simply look at this five-step sequence and understand that it is executing over and over and over, literally billions of times a second, in order to handle all of the instructions that are fed to it. And this behavior is actually hardwired into the electronic circuitry of the computer. So before I get into the five-step sequence, let me just remind you of what we covered the first week, which was the hardware of the computer. This is a picture of the motherboard. And if you recall, I told you that the CPU, which is the brains of the computer system, it is the decision maker, and then we have the random access memory, where the instructions and the data that the CPU operates on are stored. And so much of the fetch execute cycle is the exchanging information back and forth between the CPU, the brain, and the RAM, where the instructions and the data are stored in the computer. So here is the fetch execute cycle. It starts with instruction fetch, which is denoted as the abbreviation IF, and then instruction decode, denoted by ID, data fetch, DF, instruction execute, EX, and results return, and that's RR. So these are the 5 steps. This is a simplified explanation, but these are exactly what all computers do over and over and over at very high speeds in order to run software, regardless of what kind of software it is, whether it is Microsoft Word, a web browser, scratch programming. It all comes down to the same 5-step sequence that the computer executes in order to do the task that it's programmed to complete. So let me also give you a block diagram of the computer's hardware. We looked just a moment ago at a picture of the motherboard. This is a block diagram that makes it a little more makes it easier to visualize the hardware components of the computer and how they act during the fetch execute cycle. So this diagram shows the not the 5 steps of the fetch execute cycle, but it just so happens that there are 5 basic components of the computer, and they are the arithmetic logic unit, the control unit, the random access memory, the input unit, and the output unit. And we're going to look at what each of these do and how they do it during the fetch execute cycle. Actually, most of it is going to be these 3. The input and the output devices are things that we use to interact with the system. So let's start with memory. We've already talked about the idea that memory is grouped into binary digits of 8 called a byte, and we've already discussed the concept behind how the computer stores information or represents information. We've talked about numerical information such as decimal values being converted into 8-bit sequences. And we've also talked about the American Standard Code for Information Interchange, which is ASCII, which is used to encode all of the keyboard characters into 8-bit bytes. And so each of these memory locations in random access memory have their own unique identity. And we use an address to identify the location in the random access memory for each of them. And then, of course, each of the bytes can store some information, a value, a letter, or it could be some portion of information that's stored across multiple bytes. In the end, we have a finite amount of memory that we have available in our computer system. Let me give you a quick example by looking at this computer that I'm recording on. I'll show you the control panel system information, and what you'll see here is that the amount of RAM that I have for my computer is 6 GB or 6 gigabytes, and that's 6 billion bytes of random access memory that I can use to store and execute instructions with. We'll come back to this system information in more detail in a second. So another way to visualize what's going on with random access memory is to use this diagram. And it shows basically little blocks or boxes, and in each box there's some information stored. And this represents the bytes that are in random access memory. And the very first byte is given the address location 0, counting up to the next one, 1, 2, 3, 4, 5. So again, each byte has its unique identifying address, and it is capable of storing information such as a value of 100, uppercase T, lowercase h, so on and so forth. 1 byte of memory, as we've already discussed, could store an ASCII character, or it could store a number that's less than 256. We've discovered that from the information that we've covered last week. However, programmers need to be able to sequence larger amounts of data together in order to represent more complicated things like music and video. And so a common grouping would be 4 bytes at a time, or 32 bits. That's 4 times 8, gives you 32 bits of memory to store information, and we refer to that as a word. Now, some computers work on 8-byte words, which are 8 times 8 bytes each being 8 bits long. And so we work on 64-bit words. In fact, the one I was showing you here, the one I'm recording on, we actually are using a 64-bit operating system, which denotes that I have a 64-bit word. My CPU will actually operate on 64 bits at a time. And this is just some kind of an indication of the power of the architecture of my computer, is that it's a 64-bit system as opposed to a 32-bit system, which makes it somewhat more powerful and somewhat faster than other 32-bit systems. So finally, the concept of random access means that the computer can access any of the locations of the memory by using that unique address that we just talked about, and allows it then to read any particular byte or sequence of bytes starting at a known memory address. As I already mentioned, memory is generally measured today in gigabytes or billions of bytes. I suppose some systems still represent information in megabytes, which are millions of bytes. Certainly files are stored in megabytes, such as video files and things. But in general, the larger the amount of random access memory you have, the better, because the computer can run faster. So let's talk about the fetch execute cycle, and we're going to actually start to talk about the control unit, which does a majority of the steps of the fetch execute cycle. And to illustrate this, we're going to talk about a memory word that the control unit might go and retrieve from random access memory. And in this case, it looks like this: ADD space 4000 comma space 2000 comma space 2080. Now, to describe what this does, we're going to identify the components of this instruction. First, it's an ADD, or an add. That's the operation that it will perform. The next thing is the destination, where the sum, because it's an add function, there's going to be a sum that is going to be generated, where it is going to be stored in random access memory. And then, of course, to add together, we need operands. We need values to operate on. So the 2000 is source 1 and 2080 is source 2. So another way of looking at it, written out more like a math type of expression, is we're going to go to the location in RAM memory where there's some value stored. The location is location 2000. And then we're going to add the information that is stored at location 2080. Again, this is not adding 2000 and 2080. It's adding the data that is stored in the random access memory at the address location 2000 and 2080. Then there's going to be an addition operation completed, and the result of the addition, the sum, will be stored in the location 4000. Again, this is not the sum. 4000 is not the sum. It is the location in random access memory where the sum will be stored. It is this fetch step that is the control unit is responsible for. It fetches this information, then it decodes it, breaking it into its opcode, in this case, destination, source 1, and source 2. And then it goes and retrieves the data out of those locations in memory. So as an example, to illustrate this, while the instruction never changes, the data that is stored in random access memory may change if the same instruction is executed at 3 different times. So in this example, it shows at time number 1 that there is a value of 48 stored in the location in RAM 2000, and then there is a 2 in location 2080. So when we execute this instruction, we're going to add together 48 and 2, storing the result, the sum, of 50 in the location 4000. At another time, we may execute the same exact instruction, which will go and get the same, it will go get the same location, though the data there may have changed since the last time we executed this instruction. In this case, it shows that there's a 9 located at location 2000, and then there's a value of 0 located at the memory location 2080, and we're going to add those two values together and store the sum, which is a value of 9, in the location 4000. And then finally, a third time that this is executed, there may be a value, say 14, that's stored in location 2000, and a value of 14 also stored in 2080. We'll add those two together and store the sum in location 4000. So again, nothing changed in terms of the instruction. It was only the data that was fetched from RAM that changed. So again, we added the same locations, 2000 and 2080 of RAM, and stored the result in location 4000 in all 3 instances. The only thing that changed was the amount, the type, the information that was stored at the locations in RAM. So again, in this example, we were doing a simple math function of adding. The actual addition is done by the arithmetic logic unit, and it is done during the execute step of the fetch execute cycle. There's a circuit in the ALU that will allow it to add 2 numbers together. There's also circuits in there for multiplying and comparing 2 numbers. We can see if 2 numbers are equal or if one is greater than or less than the other. In some cases, all we're doing is transferring information from one location in RAM to another, and in that situation, we don't actually need the ALU. The input and output devices that are hooked up to the computer so that we as humans can interact with it are referred to as peripherals. And the wires and the circuits in the computer that connect to those devices, those peripherals, are called the input-output units. The keyboard is the example that we'll use most often as an input device. It encodes the keystrokes. So as you type in keys, we know now that these keys are represented by binary bits in the form of ASCII that then are sent into the computer circuit to represent the keys that we've struck on the keyboard. The monitor basically does the opposite. It displays information on the screen for us to see that is coming from the computer's memory. And then a couple other options are speakers for converting data into sound. We also have microphones that will do the opposite. They'll convert sound into bits that are stored in the computer's memory. And then we have disk drives or flash drives like your thumb drive that you can use as both an input and output device for storing programs and information. Now, whenever we're talking about a peripheral device such as a keyboard or a monitor or a speaker or even a disk drive, we know that these devices are actually not dumb, but we refer to them as dumb because they have to have instructions of their own in order to understand how to communicate intelligently with the computer. We refer to the software that they run as device drivers. And often these device drivers reside on the device themselves, so that as power is delivered through a connection to the device like the keyboard or the mouse or the monitor, the device automatically will read the instructions that reside on them so that they'll know how to communicate to the computer. So for an example, when we press a key on the keyboard, the ASCII symbol that represents that keystroke can be generated and sent to the computer, which